Okay, good afternoon, everyone. I'm Anthony Roblick. Welcome to Module 2 of the Stormwater Management Design Review course. We'll go ahead and get started now. Just as a reminder to everyone and to reiterate what Lisa had just said, we are recording this module as with all the modules in this course. So we ask that you please keep your microphones muted during the presentations. And if you have any questions, to please type them into the chat and our staff will respond. As another reminder, for those of you who are interested in receiving the Continuing Professional Competency credits or CPC credits for attending this course, they're based on the hour, given that there's at least 50 minutes of instructional time within that hour. So that will give us 12 CPCs for this course. So with that, here's the agenda for Module 2. In between each presentation, we'll take a quick 1 or 2 minute break before moving on to the next speaker, time permitting. And we'll begin the day with a presentation on stormwater calculations, and that's presented by myself. Then we'll move on to a soil testing presentation, and that's presented by Lisa Schaefer. And that'll be followed by a presentation from Dr. Dick McGee from NJCAT, and that'll be on manufactured treatment devices. And after those 3 presentations, we'll have a quiz 2, and then we'll end the day with a quiz review. So let's get started with our first presentation, which will cover stormwater runoff calculations. So this material is included in the course because the DEP has found from previously conducted audits of the MS4 permittees that stormwater calculations are oftentimes not performed correctly. So while most of you are probably familiar with these methods, as evidenced by incorrect calculations in some of the projects submitted for the audits, we're including this brief review in the course. So later presentations in Module 3 will highlight some of those errors more specifically, and as will the example projects later on in Module 4. So the 6 major goals of this presentation are 1, understanding the Natural Resources Conservation Service, or NRCS methodology, and that's formally referred to as TR55. And we'll be using that to calculate peak flow rate, volume of runoff, and produce hydrographs. Also, NRCS was previously known as the Soil Conservation Service, or SCS, so you may still see those acronyms, NRCS and SCS, used interchangeably. So 2, using the NRCS methodology to calculate runoff volume. 3rd goal is to calculate the time of concentration, and we'll cover some of the examples in our revised version of Chapter 5 in our B&P manual. Next, we'll take a more detailed look at hydrographs and rainfall distributions. Then we'll cover the NJDEP 2-step method for calculating runoff from an unconnected impervious area. And our last goal of this presentation we'll cover when exfiltration may or may not be used in stormwater routings. So first, we'll take a closer look at the NRCS methodology. So the requirement is found in the rules at the location noted here in green. That's NJAC 7:8-5.7A1. So the method listed here is in the rules is the USDA NRCS methodology. And it was, as I mentioned earlier, it was additionally described in TR55. However, TR55 has been superseded by the National Engineering Handbook, NEH, in Part 630 Hydrology. And a link to that is at the bottom of the slide. The NRCS method can provide total stormwater runoff volume, the peak flow rate, and produce hydrographs. And under the NRCS method, different synthetic rainfall distributions and unit hydrographs can be applied to produce the stormwater runoff hydrographs in accordance with geographical differences that may affect the rainfall pattern of each storm event and the runoff pattern in a region, which is dependent upon factors like slope and ground condition. There are plenty of software packages that use this methodology, and in later presentations, you'll learn what to check in your reviews. So the NRCS method can only be used for a drainage area, or can be used for a drainage area of any size. But the area is subject to the rule requirement that the relative stormwater runoff rates and volumes of pervious and impervious surfaces be separately considered to accurately compute the rates and volume of stormwater runoff from the drainage area. So the NRCS runoff equation was developed to estimate total storm runoff from total storm rainfall. The soil and cover conditions determine a parameter called the curve number, or CN, which will be discussed shortly. But first, we'll look into the equation that uses that parameter. So we can calculate the runoff depth Q in inches by using the NRCS equation. P is our rainfall data for a particular design storm. The next parameter is the initial abstraction, I sub A, which is the stormwater volume loss before runoff begins. It includes water retained in surface depressions, water intercepted by vegetation, evaporation, and infiltration. For New Jersey, initial abstraction is equal to 2/10 the potential maximum retention S, for which we need the curve number to calculate. After determining the curve number and calculating S, we are able to calculate the total depth of runoff. And so that brings us to a discussion on curve numbers. So the curve number, abbreviated CN, is an empirical parameter used for predicting direct runoff or infiltration from rainfall excess. CN is a function of the hydrologic soil group, or HSG, and land cover, such as woods, pasture, agricultural use, etc. HSG-A is the most permeable group and produces the least amount of runoff when thoroughly saturated. The designations go alphabetically from B to D, with D being the least permeable group and having the highest runoff potential. The preliminary soil group classification can be found on the NRCS Web Soil Survey, but further investigation may be necessary, and Lisa will cover that next in the soil testing presentation. And she'll also cover the default HSG values we may assume. So once you've determined the HSG or are using the defaults that are allowed, you can determine the curve number value to input. So shown on the right is table 9.5 from the NEH, or the National Engineering Handbook. There are many different land uses, but most of the time you'll see those in the row denoted by the arrow towards the top, which is for good condition open space. Notice the CN increases as the soil group goes from HSG-A to D. So there's going to be more runoff for a D soil than for an A soil for a given land cover. And it's crucial to use the CN value that best identifies the ground cover type and hydrologic condition. If the analysis uses pre-development CNs that are lower in value, the analysis is considered conservative. However, if the analysis uses pre-development CNs that are too high, the analysis is considered incorrect. Note the requirement from the stormwater rules shown in the yellow box at the upper left of the slide regarding which CN value to use. And the arrow on the right indicates the particular row where this CN value is in table 9.5. And this requirement also appears in the local SCO. Remember that for an impervious surface, the curve number is always 98. And lastly, note the cautionary info in the white box on the bottom left of the slide. That means that the values in the red box on the table are not what you will typically see in your calculations for development for a development project. So the next question is, what do you do when you have more than one curve number on a site? So due to the nonlinearity of the equations and losses from initial abstraction, it's important to also required in the rules to compute separately the runoff volumes from pervious and impervious areas instead of averaging the curve numbers together. Particularly for the smaller, more frequent storms, averaging underestimates the volume of runoff generated by the impervious surface on a site that also has pervious land cover. So using composite CN values is a common error that we found in our audit reviews. For example, if we analyze a site with 1 acre of impervious with a CN of 98 and 2 acres of grass lawn with a CN of 65, for the water quality design storm, using a composite CN for the site would result in roughly 70% less runoff volume than if volumes were calculated separately for pervious and impervious areas. So using a composite CN means the BMP is likely undersized for smaller storms, including the water quality design storm. And when that happens, the BMP does not merit the pre-approved rating for total suspended solids removal. So here's a better example from Chapter 5 of the BMP manual. So this states a portion of a major development consists of a 200-foot wide, 25-foot long impervious surface and a 200-foot wide, 75-foot long grass lawn area that are separated by a grass swale. The soil is identified as HSGA. The 2-year design storm produces 3.5 inches of rain over 24 hours. The slopes of the impervious surface and the grass lawn are both 1%, and it's asking us to compute the volume of runoff that is produced. So first, just to note, this example mentions the 2-year design storm doesn't make a distinction between the current or the projected 2-year storm event, and that's because it's not necessary to do so for the purpose of this example, which is just to show that for a given rainfall depth, land area, and slope, how different calculated runoff volumes can be with the different considerations. So from the example diagram, we see that the runoff from the impervious surface will flow directly onto the grass swale. And when looking up the CN for grass from table 9.5, which you just saw a few slides ago, we get a CN value of 39 for HSGA soils. And of course, the CN for impervious cover is always 98. So next, we'll calculate the volumes produced for this storm using a correct method, which is calculating pervious and impervious runoff volumes separately, and also the incorrect averaging method. So using the NRCS runoff equation, we calculate S, the potential maximum retention, using our CN values and input the rainfall data to calculate the depth of runoff, which we then multiply by the area on which it falls to compute the volumes. So for this example, look at the yellow shaded box, and averaging the CNs yields a volume that is only 37% of the total volume we calculate when following the rule requirement to compute the runoff separately. And that's shown in the green box on the left. So calculating the runoff from pervious and impervious surfaces separately yields a total runoff volume of 1373.3 cubic feet, while using the incorrect composite CN value for both surfaces yields only 508 cubic feet. So this example kind of does the job to illustrate how different the results can be and why we always use the method that's identified in the green box on the left. So moving on to the next goal, which will cover time of concentration. Previously, we saw the definition from the rules that it is the time required for stormwater runoff to travel from the most hydraulically distant point on a site to a point of analysis. T sub C is also an important parameter to get right in the calcs. So we'll take a look at the next graphic here to understand it a little better. So a site consists of one or more drainage areas, and a drainage area is a land area where all the stormwater runoff produced by that area converges to a single point. Drainage areas are sometimes also called drainage basins, which are determined by the topography. They can range in size from very small to up to millions of square miles. By looking at this watershed, you'll see that due to the slopes of the area, any drop of water that falls in the valley in between those 2 yellow shaded areas will eventually make its way to the river. And any drop of water that falls on the other side of those ridge lines it will flow somewhere else, will flow in the opposite direction. So remember that the most hydraulically distant point doesn't necessarily mean the furthest point in distance. In this image, the surrounding terrain on each side up to the ridge lines are part of the drainage area directing runoff to this point of analysis, or POA, and it's marked by the red dot. Therefore, even though runoff has to move much further in distance to get from the mountains to the outlet of the river, the most hydraulically distant point may be somewhere in the forest. So in Module 1, we learned that the various land uses, slopes, and other factors all affect how fast stormwater actually moves across the land. For example, dense vegetation like forest causes runoff to move more slowly than smoother land surfaces, and steeper slopes cause runoff to move faster. So to compute the time of concentration, surface roughness, channel shape, and slope are the three parameters that must be characterized for each segment of flow along the flow path. Additionally, the energy level of the flow also factors into the calculation. The three types of energy the flow may exhibit are sheet flow, shallow concentrated flow, and channel flow. The two most likely to occur in calculations are sheet flow and shallow concentrated flow. Most of you probably know what I mean by sheet flow, but we'll go over it just in case. So sheet flow is usually at the headwaters and over plain surfaces. This is where runoff forms a thin sheet that is low in energy, also low in velocity and depth. This is what you may see on lawns or in parking lots. In Chapter 5 of the B&P manual, we note that sheet flow does not occur after 100 feet, and there's more to cover on that in a couple of slides. Shallow concentrated flow occurs where runoff begins to coalesce and pick up velocity. The depth is greater than 1/10 of a foot and doesn't really have a defined channel yet. But lastly, channel flow can be seen in aerial photographs and on GIS and USGS maps. It is essentially flow in some type of bounded channel, which is higher in energy state and relatively faster than the other two types of flow. So now that we covered the types of flow energy, we can put them to use. So from the NEH, the velocity method can be used for a project site or drainage area. Remember that the time of concentration is the sum of all the travel times, T sub T's, for each type of flow in a segment along the most hydraulically distant flow path. You can have more than one occurrence of sheet flow, for example, because one of the defining parameters such as slope has changed. And this requires a calculation for each type and instance of flow over the segment or path in which it occurs, and then simply adding them up. Just to note, going forward, the assumed minimum value of 6 minutes previously published in Chapter 5 of our B&P manual must now be replaced by a correct calculation. Therefore, it's important to check the reported values in your reviews. If the T sub C is calculated incorrectly, it could potentially impact the neighboring land, the infrastructure, or even a local waterway. Chapter 5 also changes the maximum sheet flow length in accordance with the NEH Chapter 15. For the pre-construction condition, assume sheet flow occurs for up to a maximum of 100 feet, unless there is something physically in contact with flow of stormwater runoff, such as a swale curb or inlet, to prevent sheet flow from occurring. And that's by increasing the depth of flow in excess of 1/10 of a foot. And it's regardless also of whether the surface is impervious or pervious. So if the site conditions only create 75 feet of sheet flow, use 75. But to repeat, the max value is 100 feet. So for the post-construction condition, the maximum sheet flow length should not exceed either the McEwen-Speece limitation or 100 feet, whichever is shorter. And the equation to calculate the McEwen-Speece limitation is noted under the second bullet here, where L is the sheet flow length determined by the McEwen-Speece limitation, S is the slope, and N is the Manning's roughness coefficient. So if the sheet flow length calculated by McEwen-Speece limitation criteria is less than 100 feet, use the length determined by the calculation. If the sheet flow length determined by McEwen-Speece limitation exceeds 100 feet, the sheet flow length must be limited to 100 feet. But keep in mind, this criteria is for the maximum sheet flow length that can be used. If site conditions have a physical obstruction at a distance that is less than both either the McEwen-Speece limitation or 100 feet, then that shorter distance should be used. So now that we've covered sheet flow length limitations, we can talk a little about how travel time for sheet flow is calculated. So this is the travel time equation for sheet flow, which uses Manning's kinematic equation. And listed here are the parameters that must be identified. Those parameters are the sheet flow length, which we just talked about, Manning's roughness coefficient, the current or projected 2-year storm event rainfall depth, and the slope. In the next couple of slides, we'll go into a little more detail on the roughness coefficient and the 2-year rainfall depth parameters. So first, let's go over the roughness coefficient, also called Manning's N value. This table here is found in Chapter 15 of the NEH. It's a measure of the roughness of a surface or a measure of the surface's resistance to flow. There are different tables for each energy state of flow. So the roughness coefficients for sheet flow are organized from smooth to rough. If, for example, a site has dense grasses, we would use a Manning's N value of 0.24 in the equation for calculating the travel time for sheet flow. Note that the lower the N value, the quicker the runoff will travel. For example, impervious surfaces have a roughness coefficient of 0.011 as seen here. Also important is that the NJBMP manual states the maximum roughness coefficient for sheet flow in New Jersey is 0.4, and that corresponds to woods with light underbrush. That's also circled here in red. So next, let's discuss the 2-year 24-hour rainfall depth parameter. If you recall, I briefly mentioned a couple slides ago that we use either the current or projected 2-year storm event rainfall depth for this parameter, and that's dependent on which storm events the sheet flow travel time is being calculated for. So when calculating the travel time for current storm events, use the precipitation depth for the current 2-year storm, which, as Peter noted in Module 1, is calculated by multiplying either the NOAA precipitation frequency data server rainfall depth or the county rainfall data for the 2-year storm by the current precipitation adjustment factor for the 2-year design storm. And when calculating the travel time for the projected storm event, use the precipitation depth for the projected 2-year storm. And that's calculated by multiplying, again, either the NOAA data server data or the county rainfall data, but this time by the future precipitation change factor for the 2-year design storm. So this P2 parameter will vary depending on whether you're calculating sheet flow travel time for either the current or projected storm events. So on the slide, you can see a screenshot from the NOAA precipitation frequency data server. This one happens to be for Trenton. After navigating to the NOAA data server, we got here by selecting New Jersey, and then precipitation depth and partial duration for the time series type. You'll end up with a chart like this one, but it'll extend a little further in duration and storm recurrence interval, where you can find the column for the 2-year storm event, and then the row for the 24-hour duration. And the rainfall depth listed here is in inches. So from this chart, the rainfall depth is 3.33 inches, and that's circled in red. You can alternatively use the county data introduced in Module 1 for this storm. But then we're not done here. So now we have to multiply this rainfall depth by either the current precipitation adjustment factor or the future precipitation change factor for the 2-year design storm, depending on whether this sheet flow travel time is being calculated for the current or projected storm event. So since the site we're looking at in this example is in Trenton, we would look up the current precipitation adjustment factor and future precipitation change factor for Mercer County, which happens to be 1.01 and 1.16 respectively. And that results in a P2 of 3.36 inches for current storm events and 3.86 inches for projected storm events. So that's how we calculate P2 for a site that is located within a single county, which are most sites. But how do we calculate P2 if a site lies on a county line where portions of the site are located in 2 separate counties. So in that case, to calculate P2, we would have to first adjust each county's 2-year storm precipitation depth by either that county's respective current precipitation adjustment factor or future precipitation change factor, whichever is appropriate, and then perform an area weighted average. So as an example, if we're looking to calculate a sheet flow travel time to ultimately serve as input for modeling runoff for a current storm event, and we have a site where 1/3 of the site is located in Middlesex County and 2/3 is located in Mercer County, the first thing we would do to calculate the P2 variable is obtain the 2-year rainfall depths for each of the counties from either NOAA or the county rainfall data. So in our case, we actually use the county rainfall data, and for the 2-year storm event, that ends up being 3.35 inches for Middlesex County and 3.31 inches for Mercer County. So then we multiply those rainfall depths by each county's respective 2-year current precipitation adjustment factor, and it's current since we're ultimately looking to model a current storm event. Again, if we were looking to model a projected storm event, we would multiply those rainfall depths by each county's 2-year future precipitation change factor instead. But in our case, the current precipitation adjustment factor for the 2-year design storm is 1.00 for Middlesex County and 1.01 for Mercer County. So then our final step is to perform the area weighted average. So since 1/3 of our site is located in Middlesex County, we would multiply that adjusted rainfall depth by 1/3. And we would do something similar for Mercer County, adjusted to the Mercer County adjusted rainfall depth, multiplying that value by 2/3. And summing those values together, this results in a P2 value for current storm events of 3.35 inches. Okay, so next we'll cover how the travel time for shallow concentrated flow is calculated. So this travel time is equal to length for this particular segment divided by the estimated velocity, and that's multiplied by 3,600 for the conversion from seconds to hours. And velocity is estimated based on a site's surface condition and slope. So the value for the flow velocity can be determined from figure 15.4 of part 630 in the NEH. The velocities plotted are average values and are a function of watercourse slope and the cover condition of the channel. So this source was derived by solving Manning's equation for a wider variety of different land covers. The y-axis is our slope in feet per feet, and the x-axis is the average velocity in feet per second. So you would draw a horizontal line from your slope on the y-axis over to the condition line, and then draw a vertical line down to the x-axis to find the value for velocity. You may still see citations for a TR55 source, but remember that's been superseded. That figure was actually a simplified version of this figure. So make sure the graphical source used is the one shown here. So the last travel time we need to calculate is for open channel flow. So for this calculation, we need the length of this segment, the roughness coefficient for open channel flow, which is different from the other Manning's N value previously covered, the hydraulic radius, and the channel slope. Manning's N values for open channel flow can be obtained from standard hydraulics textbooks typically. So the hydraulic radius is equal to the cross-sectional flow area divided by the wetted perimeter, the surface of the channel bottom and sides that are in direct contact with the flow. Don't use this equation if you have flow under pressure in a pipe. That uses a different equation. And you shouldn't see this type of flow that often in stormwater calcs for development. So now let's work through an example for calculating the time of concentration. And this is an example from our BMP manual. So problem statement, for a site located in Mercer County, stormwater runoff flows through a wooded drainage area along a flow path measuring 1,000 feet in length, consisting of sheet flow over an area with a half % slope and shallow concentrated flow over an area 1% slope. And it's asking us to calculate the time of concentration using current rainfall data. So slope of 0.5% is equal to 0.005 feet per foot. And for woods, Manning's roughness coefficient for sheet flow in New Jersey is 0.4. The sheet flow length is calculated by using the formula for the McEwen-Speece limitation criterion. That's 17.68 feet. And since this example is asking us to use the current rainfall data, as we previously saw, applying the 2-year design storm current precipitation adjustment factor to the 2-year 24-hour rainfall depth from NOAA, and that results in a P2 of 3.36 inches. But for sheet flow length, it wasn't mentioned in the example statement, but there's actually a physical obstruction on the site that limits sheet flow length to 15 feet. So we're not going to use the larger distance, 17.68 feet, that was calculated by McEwen-Speece, but instead use the smaller distance of 15 feet, which represents the actual site conditions. So plugging all this into the equation shown here yields a travel time of 8 minutes. So remember, the total flow path is 1,000 feet. And since the sheet flow segment length was determined to be 15 feet, the length of the shallow concentrated flow must be the remaining 985 feet. The value for the flow velocity can be determined from figure 15.4 mentioned earlier. For this example, a horizontal line is projected across from the y-axis at the tick mark denoting the 1% slope to the curve representing forested areas. And the corresponding velocity is 0.25 feet per second. This value is then entered in the equation for the travel time for this segment, and that comes out to 65.5 minutes. So our answer for a time of concentration is the sum of the travel times for all of the segments along the flow path, which is 73.5 minutes. Okay, next we'll discuss developing hydrographs, which we defined earlier as the graphs depicting the flow rate of runoff versus the time passed at a specific point of analysis. A hydrograph can provide much information about stormwater runoff, including the time of concentration, the time at which peak flow occurs, the peak flow rate, and the volume of runoff generated. So first, we have to talk about the unitless and synthetic hydrographs for the NRCS methodology. A unit hydrograph is a direct runoff hydrograph resulting from 1 inch of excess rainfall. The unit hydrograph influences the shape of the runoff hydrograph, particularly the peak rate of discharge. Given a watershed's unit hydrograph, one can calculate the theoretical hydrograph for any storm event. In an ideal world, a unit hydrograph would be developed by metering the flow from a watershed, but since this isn't very practicable, we use the synthetic hydrographs instead. So 2 synthetic hydrographs were developed for determining runoff from watersheds. The 2 that we generally use are the Soil Conservation Service SCS dimensionless unit hydrograph and the Delmarva dimensionless unit hydrograph. And most software packages have settings that allow selection of either of these. So first, let's talk about the SCS, which is based on an average of natural watersheds with various sizes and geographic locations, which allow us to predict how an unmetered watershed will react to rainfall. And it's important to note that within the state of New Jersey, the SCS unit hydrograph is often outside the coastal plain, except in rare circumstances. So shown here with an orange curve is the SCS unit hydrograph. The corresponding rainfall event is shaded in blue. As you can see, the timing of the hydrograph is based on the time of concentration on a site, which is highlighted in yellow. There's some runoff at the start of the event, but and more and more areas upgrading, upgrading of the point of analysis start to contribute. After the T sub C, the furthest away areas stop contributing, and runoff continues to taper off. And the volume of runoff produced by the site in response to the rain event is equal to the area under the hydrograph. So in development of this runoff hydrograph, the runoff discharge is nonlinear in relation to the time of the rain event in accordance with NRCS observations from many natural unit hydrographs developed for various watersheds. The dimensionless unit hydrograph that was developed has a peak rate factor or a shape factor of 484, which means that 48.4% of the total runoff volume is discharged before the peak time, and that's shaded in purple. And the remaining 51.6% of the total runoff is discharged after the peak time. And the peak rate of runoff is the maximum height of the hydrograph. You can usually see the shape factor on the printouts provided in stormwater reports. So that's something to check in the reviews. The second commonly used dimensionless unit hydrograph is the Delmarva unit hydrograph. The Delmarva hydrograph is suited for the flat coastal areas in Delaware, Maryland, and Virginia, which is where it's got its name, and also those same areas in New Jersey. So shown here is a comparison of the SCS and Delmarva unit hydrograph. When calculating the peak flow using the Delmarva hydrograph, we use a constant shape factor that is lower than that for the SCS unit hydrograph. If we broke down each individual equation to develop the Delmarva, its shape factor is around 284 or 285, depending on the software used. The Delmarva unit hydrograph will not affect the determination of runoff volume, but should result in a lower peak discharge when compared to the SCS unit hydrograph. The lower shape factor for the Delmarva hydrograph means there is less runoff under the rising limb, so the hydrograph is a bit shorter in height, but it's also longer in duration. This comes well in part to the from the gentler slopes of the terrain and the lower level of urbanization where this hydrograph is typically used. So the Delmarva dimensionless unit hydrograph must be used in calculating pre-construction and post-construction peak flow rates for the current and projected 2, 10, and 100-year design storms in the coastal plain region of New Jersey, again, except in very specific circumstances, which we'll cover in a couple slides. Also note that if the Delmarva is used in the pre-condition, it must also be used in the post-condition, and that's likewise for the SCS. Projects which lie on or near the boundary between the Piedmont and coastal plain regions should be modeled with both the standard and Delmarva unit hydrographs and results compared with actual field conditions to determine which unit hydrograph offers the best fit. And so where is that boundary exactly? This is a zoomed in view with a few points of interest to the map from the previous slide. The blue line dividing the state is the boundary between the coastal plain and the Piedmont region. And a hyperlink here is to the Bureau of Geologic Information Systems for the physiographic province metadata. So you want to be careful in outlining parts of locations near the border of the coastal plain. For example, parts of Princeton, Monmouth Junction, and a little bit northwest of Trenton. The municipal stormwater management plan, where a site is located, may include this information as well. However, your best bet in determining whether a site is in the Piedmont or coastal plain regions of the state may be to use the application shown here. So this is a GIS layer noting the different physiographic provinces within the state. And this is from the DEP Bureau of GIS website. So this allows the user to look up the actual site address to very easily make a determination as to which physiographic province the site falls in. And the link noted here at the bottom of the slide is to this GIS application. So when not to use the Delmarva dimensionless unit hydrograph, the Delmarva DUH must not be used outside the coastal plain of New Jersey. For another instance, use of the Delmarva unit hydrograph is not allowed when sizing manufactured treatment devices because it will underestimate the flow rates. And lastly, when a site is within the coastal plain and the design engineer can prove to the satisfaction of the review engineer that the conditions for applicability of the Delmarva unit hydrograph are in no way present anywhere in the watershed. For example, if the site is completely paved, or there are very steep slopes present on site greater than 10%. In addition to the rainfall depth data, we have to know how rain falls during a storm event if we're going to create models and design BMPs to address runoff. To achieve the goal of estimating a rainfall event for design and planning purposes, between 1961 and 1977, NRCS developed synthetic rainfall distributions from historical records for the different regions of the country. And the basic shape of the distributions all assume that rain starts gently and then increases in intensity and then tapers off. The type 3 distribution was previously used for about 20 years. Now we require use of the NOAA C and D distributions, depending on which county we're in, per the 2012 bulletin from NRCS. So a coworker has done some modeling using these, and we've learned that you can expect to see slightly higher peak flow rates when using the C and D rainfall distributions. So here's the map of the Northeast US depicting the regions, and the bottom left corner shows a zoom in on New Jersey. This figure is from Chapter 4 of the NEH and is also included in Chapter 5 of the BMP manual. You can see the orange shaded areas will use the NOAA C distribution, while the yellow shaded areas use the NOAA D distribution. You should be able to download text data using this hyperlink. And we've also added a link to make this information available as an Excel file from the DEP webpage. Okay, so the next objective, an important approach to managing stormwater runoff is new impervious cover that is not directly connected to a site's drainage system. And this is now extra important with the GI requirements of our current rule. Again, if you have any questions as we go through this section, if you could please submit them in the chat and someone will respond. So to slow down runoff generated by impervious surfaces, certain key aspects must be addressed. Runoff from unconnected impervious areas must undergo sheet flow onto adjacent pervious areas, where a portion of the impervious area runoff is given an opportunity to infiltrate into the soil without causing erosion and further sediment transport to whatever's down gradient. Under certain conditions, this technique can help in providing both groundwater recharge and stormwater quality treatment for small rainfall events, as well as reduce the overall runoff volume that is to be treated and or controlled in a down gradient BMP. So there are 5 conditions that must be met for an impervious area to be considered as an unconnected impervious surface. Here are the first 2 conditions, and it's basically saying that the runoff must enter the pervious area as sheet flow, and it must remain that way. And the other 3 conditions ensure stability and maintain the sheet flow. For this reason, there is a limit on the steepness of the slope to 8% in the down gradient pervious area. So there are 2 methods that may be used to calculate runoff from unconnected impervious areas, and there are 3 additional requirements applicable to either method. And the 2 methods are the NRCS composite CN with unconnected impervious from Chapter 9 in the NEH, which has a 30% limitation on the impervious to the combination of impervious surfaces and receiving pervious surfaces. And then there's the NJDEP 2-step method, and that's what we're going to cover now. So as an example of the 2-step method, we've got sheet flow over the impervious surface of 25 feet, which doesn't exceed the maximum allowed flow path length And we have 75 feet of sheet flow over the down gradient impervious area, which meets the minimum requirement of 25 feet. We use the NRCS runoff equation from earlier to compute the volume generated by the impervious area. And that comes to 1362.5 cubic feet. And the next step is to assume this runoff is evenly distributed as rain falling over the adjacent pervious surface. And so to begin that step, we take the runoff volume produced by the design storm falling on the impervious area, in this case, the current 2-year storm event, and we divide that divide that volume by the area of the down gradient pervious surface to get rainfall depth, and converting units as necessary. We then take that rainfall depth and add it to the current 2-year storm rainfall depth, which also falls on the pervious surface. And that gets us a total effective rainfall depth of 4.59 inches for this example. So now we can use the NRCS equation for the pervious area, inputting this total effective rainfall and the appropriate on-site retention S to get the effective depth of rain falling on the pervious area. And then we can then convert that effective depth to effective volume by multiplying by the pervious area. And so in this case, we get 156 cubic feet, which is a pretty good amount of reduction in volume. And for a final objective in this presentation, we'll briefly go over some of the other updates to our BMP manual chapter 5. There's quite a bit of material on these next slides, so you definitely want to read through chapter 5 on your own, as this is only going to be a brief overview. But here are the first requirements for using exfiltration in routing calculations, as listed on pages 7 and 8 of chapter 5. Exfiltration is only allowed for certain small-scale GI BMPs that infiltrate runoff. All soil testing must follow chapter 12 requirements, and that'll be discussed further in the next presentation. Also, all design criteria as provided in the respective chapter of the BMP manual must be followed before the BMP can be approved. Another point is pre-treatment. It must be included unless otherwise so stated in the BMP manual. An exception would be for those really small scale BMPs where the drainage areas are less than or equal to an acre. But let's talk a little about the pre-treatment requirement, because that extends beyond just being a requirement for using exfiltration in the routing computations. So each of the subchapters in chapter 9 were revised, as some of you may know. Chapter 9 is now the BMPs that are small in scale and also meet the definition of GI because they allow stormwater to be treated through vegetation or soil, provide for reuse or infiltrate runoff into the soil. There are BMPs in chapter 10 which are also GI, but they're larger in scale and only to be used to meet the stormwater runoff quantity requirement. Their use and limitations are detailed in the summary on their respective chapter cover pages, so you can take a look at that. And they're also listed in table 5.2 in the stormwater management rules. So finally, there are BMPs in chapter 11, and they're not considered GI, and they're listed in table 5.3 of the rules. Accordingly, pretreatment is an important design criteria. If you do not see pretreatment listed under the basic design criteria for a particular BMP, it's under the type-specific design criteria. Roof runoff can be treated by certain measures listed here, and on the pages listed in the bulleted text. Here are some graphics. These are taken from chapter 9.1, and they show the different devices that can be used to pre-treat roof runoff. So the requirement for pretreatment of roof runoff can be waived under the conditions listed here. For example, a building that is significantly taller than any surrounding trees and doesn't have a vegetative roof should not need the pretreatment. However, in making this determination, the review agency must consider the mature height of any surrounding trees. When using another BMP for pretreatment, it must be designed in accordance with the design requirements outlined in its respective BMP manual chapter. Always check the BMP manual for the specifics. Roof runoff that is commingled with surface generated runoff must be treated per the manual. For subsurface infiltration basins, pretreatment may consist of any of the BMPs found in the manual, and 80% TSS removal by the pretreatment is required. Another point, small-scale bioretention systems designed to infiltrate that have flow entering as sheet or overland flow may alternatively use a 5-foot wide gravel or stone strip to filter runoff instead of the other forms of pretreatment. So back to the requirements for using exfiltration. So where can't you use exfiltration? Exfiltration cannot be used with any under-drained BMPs because exfiltration is a removing of runoff volume from the system, and under drains, of course, don't allow that. Also, for those sites in special areas or that have no runoff leaving the site in the pre-construction condition, exfiltration can be used for an entire storm under these conditions. You must determine which is the maximum storm for which no runoff leaves the site in the existing condition, or if infiltration. Last point is if infiltration is of the entire storm is required by law or rule established by the Pinelands Commission, the Highlands Council, or other stormwater review agency that has jurisdiction over the project. So groundwater mounting analyses are required when using exfiltration in the routings. These are the conditions that also apply. Basically, soils must be tested in accordance with Chapter 12 of the BMP manual, and you must follow Chapter 13, which is specifically about groundwater mounting analysis. And here are some additional things you need to know about groundwater mounting. The groundwater mounting analysis has determined that an adverse impact will occur if the resulting groundwater mound reaches the bottom of the BMP, or if the temporary localized increase in the water table encroaches upon a building or other subsurface structure, including septic systems. When an adverse impact is the result, further modifications to the size of the infiltration area of the BMP or reductions in the exfiltration rate must be performed until the adverse impacts are eliminated. A groundwater mound that reaches the bottom of the BMP means that the hydraulic gradient is reduced, which is another way of saying that the BMP cannot infiltrate runoff as fast as originally expected. So you'll have to redo the routing calcs to calculate new peak flow rates. We're not going to run through that here, but you can refer to Chapter 5 of the BMP manual for the methodology to be used, specifically examples 5.6 and 5.7, and they begin on page 47 of that chapter. Groundwater mounding is itself actually a presentation in Module 3, so we'll take a deeper look later and go through some examples there. But meanwhile, we have to finish up on the calculations and methods covered in Chapter 5. So if you haven't read it, Chapter 13 includes many more groundwater mounting examples. Even the revised version of Chapter 5 includes examples with groundwater mounting analysis and using exfiltration rates. Here's my contact info. Changi, are there any questions in the chat?
No, I don't see any question in the chat, but so we can take 5 minutes break, and if you have question, you can still type into the chat. So now it's we will come back around 2:05. Thank you.
Hello, everyone. The time is now 2:05, so we'll get started with the next presentation. So as most of you know, I'm Lisa Schaefer. I'm one of the environmental engineers here in the Municipal Stormwater Engineering Unit. And I'll be presenting, obviously, the soil testing requirements, which are now found in Chapter 12 of the BMP manual. I do apologize if I seem to go through it quickly, but I will, I'll try to be as thorough as I can. So understanding the character and saturated hydraulic conductivity of surface and subsurface soils at a proposed land development site is crucial to the design of stormwater BMPs that meet the requirements of the stormwater management rules. So I'll be going over the soil testing requirements and what is to be submitted with regards to soil testing in the stormwater management report for a major development project. So before I go further, it's also important to mention that as part of our audit experience, soil testing has been one of those areas that we have often found was done incorrectly. So this presentation will cover the information that is found in Chapter 12, and that includes the reasons why soil testing is needed, testing to determine the hydrologic soil group, or HSG, soil testing for infiltration BMPs, soil testing for seasonal high water table determination, soil testing requirements for construction and post-construction, and what information is to be submitted in a soil testing report. So there's a misconception that soil testing is required only when an infiltration BMP is proposed. And actually, soil testing is more than determining the saturated soil hydraulic conductivity. Soil testing also includes finding the hydrologic soil group, the seasonal high water table, and of course, the soil series present on a site. So the identification of the correct HSG is essential to performing accurate calculations for volume and peak flow rate of runoff, regardless of the BMP being designed. And also many BMPs require separation from the bottom of the BMP and the seasonal high water table. So for example, in a small scale infiltration basin, the 2-foot separation from the seasonal high water table should be measured from the bottom of the sand layer. For a large-scale bioretention system, say one with an underdrain, go to page 11 of chapter 10.1, where it specifies that the seasonal high water table must be at least 1 foot below the bottom of the gravel layer, inside which is the underdrain pipe itself, and that is sitting on at least 3 inches of gravel. So if there's no soil testing report showing the depth of the seasonal high water table, the reviewer will not be able to judge if this design criteria has been met. Furthermore, when using the groundwater recharge spreadsheet to calculate the annual groundwater recharge and the deficit, one needs to know not only the HSG, but the soil series that is present. Details on this will also be included in Module 3. Now, lastly, saturated hydraulic conductivity is used in BMP design and for the input parameters in a groundwater mounting analysis. So we're going to take a look at the soil testing requirements for each of these. So the first topic is the determination of HSG, which is used in the selection of the runoff curve number that's developed by the Natural Resource Conservation Service, or NRCS. And there are 3 methods used to determine HSG. So for the NRCS web soil method, you will go to the web soil survey at the link shown here. We'll go over that shortly. And then there's the default method, which I'll cover, and then the actual HSG testing procedures from subsection 1C in chapter 12. Okay, so before we go through each of these methods, we're going to touch on using those old paper versions from the county soil surveys. We checked with the NRCS and they indicated that they're no longer updating those old documents. The NRCS further indicated the web soil surveys contain the most up-to-date information. So therefore, we're requesting paper-based information be verified with the web soil survey. So that means The NRCS Web Soil Survey is the first source to be consulted for the HSG information before using the second and third methods. And by the way, NRCS has soil maps and data for about 95% of the nation's counties, so you should be in a good position to use that. Okay, so the Web Soil Survey is fairly user-friendly, and that makes it pretty easy to check the accuracy of information submitted for your review. Plus, I'm going to go through how you get this, because if the information was admitted from this submittal packet, getting it for yourself allows you to continue checking some other parameters used in stormwater calculations while you wait for them to get everything else up to submittal standards. Okay, so to get started, once you're on the Web Soil Survey website, click the Start WSS button. And after you click it, you'll start with the Area of Interest, or AOI, and that tab is circled in red on the left, and then either zoom in to the project location using the icons in the yellow oval, or click on the address that's in the area of the page located by the green arrow, and then of course enter the address. Okay, then use the AOI icons that are now in the turquoise oval to either draw a rectangle or a polygon around your site. Personally, I like to check the accuracy of my polygon against the property survey to check that I got the entire area. All right, the area information will then appear under the AOI Properties pull-down menu on the left of the screen above the quick navigation menu. Now, the next tab you'll click on is the Soil Data Explorer tab, which is one of the yellowish or tan tabs, and until it's active, and then it will turn brown. And I've added that darker blue oval to show you where to find it. Okay, next, you're selecting the soil properties and qualities, and that's the light blue oval on this slide. And then click on the pull-down menu for the item labeled Soil Qualities and Features, located next to the green arrow here. And then scroll down to find the hydrologic soil group, and that's the brownish bar located to the left of the turquoise kind of arrow. So the orangey outlines that you see on the right side of the slide are the individual soil mapping units, and those can be defined as a collection of areas defined and named the same in terms of their soil components, that is series or miscellaneous areas or both. Each map unit differs in some respect from all others in a survey area and is uniquely identified on a soil map. So by following the steps, we will see on the next slide that by clicking on the pull-down menu for the HSG, you'll get the option to select the View Rating button that's inside the black oval. All right, now what will happen next is you'll see a table listing the HSG for the soils within the selected area. They're all listed by the soil mapping unit. This table is the white area on the bottom right of the slide. All right, the top row in the table, which you should be able to see, is Fort Mott Loamy Sand, and that has a rating of A and covers the area shown on the right side of the table here. The second row is Galloway Loamy Sand, and we see a double rating in the table here. Okay, so dual HSG ratings such as A/D, B/D, or C/D, they kind of have a special connotation. The first letter applies to the drained condition, and the second letter applies to the undrained condition. The appropriate choice of HSG will depend on whether or not the site has been drained. So further investigation will be necessary, and I'll discuss this later. So if we move down the table, we get to where I've superimposed a light greenish gray rectangle on the two areas for which there's no rating. Okay. These rows correspond to the two areas of the graphic inside the dashed red ovals that are also filled with the grayish green shading. So keep in mind that when there's no rating, other steps will have to be taken. And a lack of rating often happens in urban areas where the soil might have been disturbed or the area has been filled with construction materials. So for those instances where there is no HSG rating, the soils in the undetermined HSG and soil series must be determined by the two methods that I'll cover next. So those are the default method and the procedures from subsection 1C in chapter 12. So one more thing I want to note is that if it's known that the site has been filled with construction materials or debris or anything other than the soil shown in the soil survey map, you cannot solely rely on the HSG information shown on the web soil survey. You'll have to use the other methods to determine the hydrologic soil group. So where HSG information from the soil survey is unavailable, default values for HSG may be used for runoff computations for pre and post development conditions. So we know that HSGs in urban areas are often unknown. So we often use these default values in these areas. So in the coastal plain, the pre-developed condition HSG to be used is that of A, but you use HSG-D for the post-developed condition. And outside the coastal plain, use HSG-B for the pre-developed conditions, but once more, use HSG-D for the post-developed conditions. So Anthony showed us on the previous presentation how to view on a map the physiographic provinces in New Jersey and where the coastal plain is found. So here's the link again to the Bureau of GIS for their interactive website. And you can now enter a location to find out in which province an address is located. So here's what, when you first look at the screen, this is what you're going to see. And this page is interactive, so you can zoom in enough to differentiate between two houses on the street. Here's 401 East State Street next to the green arrow. And you can see that this site is in the Piedmont province. Okay, the lighter blue area right down here in the corner, that's the coastal plain. And I think you'll really appreciate how easy it is nowadays to check whether a project is in the coastal plain. So if you don't want to use the default HSG values, soil testing must be used. And the third bullet on this page, the solid bullet, is a quote from Chapter 7 of the NRCS National Engineering Handbook. All right, and that states that the assignment of HSG is determined by the water transmitting soil layer with the lowest saturated hydraulic conductivity and depth to any layer that is more or less water impermeable, such as fragipan or durapan, or depth to a water table if it's present. The least transmissive layer can be any soil horizon that transmits water at a slower rate relative to those horizons above or below it. Now you may use the links shown to view Chapter 7. So we're going to go to their table 7-1 from page 112 in that chapter. And the table relates saturated hydraulic conductivity to the hydrologic soil group. Okay, so there's a lot going on this slide. First, we've got table 7.1 from the NEH. And again, we are going to determine the hydrologic soil group from the depth to a water impermeable soil layer that has a saturated hydraulic conductivity of 0.0014 inches per hour or less. Or we're going to look at the depth to the seasonal high water table and the saturated hydraulic conductivity of the most restrictive soil layer within the depth to a water impermeable layer. So I've got a quote here on the page that I'm going to read for you. Certain wet soils are placed in Group D based solely on the presence of a water table within 24 inches of the surface, even though the saturated hydraulic conductivity may be favorable for water transmission. If these soils can be adequately drained, then they are assigned to dual hydrologic soil groups, A/D, B/D, and C/D, based on their saturated hydraulic conductivity and the water table depth when drained. The first letter applies to the drain condition and the second to the undrained condition. For the purpose of hydrologic soil group, adequately drained means that the seasonal high water table is kept at least 24 inches below the surface in a soil where it would be higher in a natural state. So in our table, the HSG designation is in the right-hand column. If the depth is less than 20 inches, the soil is classified as D per the top row in the table. Where the depth to the water impermeable layer is 20 to 40 inches, we look in the table in the area of the red oval. Then, if the depth to the high water table is less than 24 inches, we would look at the rows to the right of the orange oval. So this is where we would find the appropriate saturated hydraulic conductivity range for the least transmissive layer within the corresponding depth range for the site conditions. So continuing on with the testing procedures, the presence and depth of restrictions must be included in the soil logs for each soil profile pit and boring. On the left is a soil sample log showing the depth to the restrictive layer, and the seasonal high water table is also shown with that blue line. On the right is a shallow soil pit with a face that's been cleaned and prepped for describing the soil profile pit. So it's not in New Jersey, this one's from Alaska, but it was dug to the depth of the permafrost, which was only about 15 inches. All right, next, we're going to look at the required number of soil profile pits and soil borings that are required for soil testing that is performed to determine HSG. So for each soil mapping unit that is less than 0.5 acres, 1 pit and 1 boring are required. For each soil mapping unit that is between 0.5 and 2 acres, 1 pit and 4 borings are required. And for each soil mapping unit greater than 2 acres, 1 pit plus 1 pit per each additional 2 acres, and 4 borings plus 2 more borings per each additional 2 acres are required. So the placement of soil profile pits and soil borings is also an important part of this requirement. Soil profile pits and borings should be completed equidistant apart within the boundaries of the mapping unit to provide adequate characterization. So let's look at these two examples. So for the pink area, which is 2 acres in size, we see 1 soil profile pit and 4 borings, and this configuration meets the placement criteria. Okay, for the 6 acres area on the right that's in the green shading, we see 3 pits and 8 borings. Okay, that's 1 soil profile pit and 4 borings for the first 2 acres, and then 1 soil profile pit and 2 borings for each additional 2 acres. And so this configuration also meets the placement requirement. Okay, now there's also a depth requirement in the determination of hydrologic soil group. So in the previous version of this chapter, when it was Appendix E, we had a depth of 6 feet that was required. But now Chapter 12 just requires at least 40 inches. Okay, the presence and depth of soil classification must be included in the soil logs. And I think that pretty much covers the soil testing requirements for determining HSG. Now, we also have a workbook that we've created for you, and you can download it from the website if you want. And what's shown here is the first worksheet in that workbook. In the top part, you will enter the size of each mapping unit, and the spreadsheet then calculates the number of soil profile pits and also the number of soil borings required. So the results are displayed in the columns filled with the yellow color. Okay, the lower part of the worksheet can also be used to calculate the depth of a soil profile pit or boring. So based on the information you covered, in the event that the seasonal high water table is within 24 inches, a message will be displayed indicating that there are HSG-D soils. Okay, so that brings to a close the part of the presentation for determining HSG. Next are the soil testing requirements for infiltration BMPs, which is found in section 2 of chapter 12. So first of all, by infiltration BMPs, we mean a BMP that infiltrates runoff into subsoils, including such BMPs as, of course, infiltration basins, but also sand filters, bioretention basins, and pervious paving systems designed without underdrains. So testing for BMPs with underdrains will be discussed later. All right, so let's first look at the number of soil profile pits and soil boring requirements for any infiltration BMP. So knowing where the seasonal high water table is located is essential. A minimum of 2 soil profile pits must be excavated within the infiltration area of any proposed infiltration BMP to determine the elevation of the seasonal high water table and to test the hydraulic conductivity of the most restrictive horizon between the basin bottom and the seasonal high water table. Placement of the test pits must be sufficient to provide adequate characterization of the infiltration area. For BMP infiltration areas that are larger than 10,000 square feet, a minimum of 1 additional soil profile pit must be conducted for each additional area of 10,000 square feet. And at least 1 test to establish the soil hydraulic conductivity must be conducted for each soil profile pit. Okay, so to verify the location and numbers of the soil profile pits, you as the reviewer need to see a site plan depicting the location of the soil profile pits that are and make sure that they are within the infiltration area of the proposed BMP. So here's one example of determining the number of soil profile pits needed for an infiltration BMP with a bottom area measuring 100 by 250 feet. So that's 25,000 square feet. All right, so for this infiltration basin, we need 2 profile pits for the first 10,000 square feet, which, since the basin is 100 feet wide, translates to 100 feet of the length as marked here, plus 1 for each for the additional 10,000 square feet in the middle section, plus 1 more for that extra 5,000 square feet on the right end. Now, the next few slides will look at the number and location of tests for special types of infiltration BMPs. We'll look at the requirements for small scale and then linear BMPs. And after that, we'll go on to other tests we need to perform for all infiltration BMPs. All right, so soil testing for small scale infiltration BMPs. So when we have 1 or more of these BMPs that include our small scale GI BMPs or dry wells, we need 1 soil profile pit for each soil mapping unit where the multiple BMPs are located, plus for each BMP with an infiltration area less than or equal to 500 square feet, we're going to need 1 soil boring at each BMP. Then for each BMP with an infiltration area that's greater than 500 square feet, we're going to need 2 soil borings at each BMP. And lastly, for small scale GI BMPs that are arranged linearly, we're going to need 1 soil boring at each BMP and 1 soil profile pit for every 2,000 feet of length. All right, and now for our linear infiltration BMPs. So to be a linear infiltration BMP, all 3 of the bulleted criteria must be met, and this information is found on page 15 of chapter 12. So for linear infiltration BMPs, a minimum of 1 soil profile pit must be conducted within each soil mapping unit. In each soil mapping unit, the soil profile pit must be conducted within the first 500 linear feet of the BMP. And where the length of a linear BMP exceeds 500 linear feet, 1 soil boring must be conducted at every 500-foot interval, and 1 additional soil profile pit must be conducted for every 2,000 linear feet. All soil explorations must be equidistant to adequately characterize the infiltration area. Okay, so let's do some examples for linear infiltration BMPs. And we have 2 sites. The first one is shown on the top of the slide, and it has 2 soil mapping units. So we must include one pit for a linear BMP 500 feet in length that's shown in the soil mapping unit shaded in yellow. And then we need one pit for the first 500 linear feet of the green shaded soil mapping unit, with one boring for each additional 500 feet portion. And as long as 2 pits and 3 borings are performed, this example meets their requirements. For the second example site, there's a linear infiltration BMP with a total length of 2,500 feet, all within one mapping unit. So what's needed in this case is the required pit for the first 500 linear feet, followed by one boring for each additional 500-foot increment, and one more pit for the additional distance that's 2,000 linear feet after the first 500 feet covered by the initial pit. So these examples are in Chapter 12 as figure 12-4, right, for you to refer back to. And I always have to go back to these, so you are not alone. All right. So continuing on with the other soil tests needed for infiltration BMPs, there are the tests to determine soil hydraulic conductivity, depending on whether or not soil replacement is proposed. So for the scenario in which no soil replacement is proposed, after determining the numbers and locations of the soil profile pit for the infiltration BMPs, you have to decide the depth of the soil profile pit. And then there's the question of which soil layer to select for performing the test for soil hydraulic conductivity. This testing must be conducted on the most hydraulically restrictive horizon or substratum above the seasonal high water table or non-fractured bedrock, but located below the lowest elevation of the BMP and above whichever of the following depths is greater. Okay, that's 8 feet below the lowest elevation of the BMP, or to a depth equal to twice the maximum potential water depth in the BMP measured from the lowest elevation of the BMP. So if soil replacement is proposed beyond the required layers in the BMP, the depth is measured from the elevation of the bottom of the required sand or soil layer. So this requirement means first, the excavation of the soil profile must reach to the required depth, and second, the hydraulic conductivity must be tested on the most hydraulically restrictive soil layer below the soil replacement or the lowest point of the basin, but above the required soil profile depth. Okay, so please note that the depth requirement of whichever is greater, that is 8 feet or twice the maximum water depth, is measured from the lowest point of the basin bottom or from the bottom of the soil replacement, whichever is deeper. Very often, we've seen the hydraulic conductivity test is performed at the top of the soils to be replaced, but doesn't include the depth of the replacement. That's the wrong place to do this. Okay, up next is a discussion of what test methods are acceptable for this type of soil testing. So soil hydraulic conductivity can be determined using a tube permeameter test, a percolation test, a single ring infiltration test, a basin flooding test, or a modified basin flooding test. Please read the specific conditions that are published in Chapter 12 under which these tests can be used. So additional methods of establishing the soil hydraulic conductivity, such as ASTM D3385 double ring infiltrometer and USBR 7300-89 well permeameter method, or other soil hydraulic conductivity tests that utilize in situ conditions and are accompanied by a recognized published source reference can be used, such as the Guelph permeameter or the Philip Dunn permeameter, available at the Soil Science Society of America book series 5, I believe is the publication, and it's called Methods of Soil Analysis, Part 1, Physical and Mineralogical Methods by Clute, and it dates back to 1986. So when you're performing a soil boring during the soil exploration, the soil borings must be performed and reported in accordance with ASTM D 1452, Practice for Soil Investigation and Sampling Auger Borings, and ASTM D 1586, Test Method for Penetration Test and Split Barrel Sampling of Soils. Sampling must be continuous for the entire depth of the soil boring to fully characterize the soil profile. Since the actual saturated hydraulic conductivity rate may vary from soil testing results and may decrease over time, a factor of safety of 2 must be applied to the slowest tested saturated hydraulic conductivity rate to determine the design saturated hydraulic conductivity rate, and that's what is used to compute a BMP's drain time for the maximum design volume. The exfiltration rate for a BMP allowed to use exfiltration in the routing calculation, or the recharge rate in the groundwater mounding analysis. Okay, now where any tested saturated hydraulic conductivity rate is 20 inches per hour or more, the maximum that you can use for the design saturated hydraulic conductivity rate is 10 inches per hour. So the test procedures and the conversion equations for the tests shown here are available in Chapter 12 of the BMP manual. And there are also worksheets for some of these, okay? So you will find the PERC test on page 30, 2 permeameter test, the basin flooding test, the modified basin flooding test, and the single ring infiltration test at the pages where noted in this table. All right, but the cased borehole infiltration test is suspended for further assessment, and don't use this until further notice is provided from us. So for the double ring infiltrometer, the well permeameter, and other permitted testing methods, you can obtain them from the American Society for Testing and Materials, or the organization that's publishing the test method. For the PERC test, follow the procedures described in Chapter 12, and the field measured hydraulic conductivity value shall then be calculated using this simplified equation, and again, it's in Chapter 12. I want you to take note that although the test step 4B in the test procedure for a PERC test requires one to fill the water to a depth of 7 inches, the time of recording is started when the water level drops to 6 inches. Okay, not 26, but down to 6 inches, and stopped when the water in the hole has emptied. Okay, so you fill it, you watch it. When you hit 6 inches, you go. The second worksheet in the Excel workbook may be helpful for your recording for hydraulic conductivity testing. All right, on the left is the top and middle portion, and it's rather long, so the other part's on the right side of this slide, okay? So you have the number of profile pits and borings required, depending on the type and size of the BMP, okay? And the stuff on the right gives you the depth of the testing. Moving on, next is soil testing to determine the seasonal high water table. So you're going to see it often abbreviated in our text, and here as SHWT. So pursuant to Table 5-1 in the Stormwater Management Rules, this testing is not applicable to BMPs such as blue and green roofs, as they're constructed as above grade BMPs, plus the others where no separation is listed in this table. So testing to determine the location of the seasonal high water table is required for BMPs with underdrains, for grass swales, and of course, as can be expected, BMPs designed to infiltrate. Now, this section of the chapter never stated that underdrain BMPs were excluded. So that's why we're clarifying this issue. So, all right, for BMPs designed to infiltrate, you have A and B here. You follow the guidance and test at least 2 areas within the footprint the bottom area where the infiltration will occur. And for non-infiltration BMPs, you test within the area to be occupied by the BMP, and otherwise the number of tests required follows the requirements for infiltration BMPs. So one other thing is if you're getting inconsistent results in your tests, or you're seeing such inconsistencies when you're reviewing the soil testing data, then you're either going to perform or require more testing as the case may be. Okay, so for the soil testing for seasonal high water table, I have a little graphic that may help illustrate when certain testing and resource data may be used. All right, so this is a new slide that hasn't been in other presentations because I know that some people like to look at pictures. I am one of those people. I certainly enjoy drawing them. Okay, but this will helpfully help clarify some misunderstandings about when to perform soil testing to locate the seasonal high water table. When you set out to determine the location of a seasonal high water table, there's a sharp divide on how you determine where it's located. And this is based on your observations, meaning the features that you see. So the next few slides will cover more in detail what's summarized in this graphic. We're going to start with the simple case, meaning what applies when the answer to the question of whether modeling is observed is yes, the bottom row. So where redoxamorphic features such as modeling are observed at any time of the year, the seasonal high water table shall be taken as the highest level at which those redoxamorphic features are observed, except when the water table is observed at a level higher than the level of the redoxamorphic depletions or concentrations. And for details on determining whether saturated soils are present, the guidance document published by the NRCS, Field Indicators of Hydric Soils in the United States, may be used. Okay, where modeling is not observed, the seasonal high water table shall be determined as followed, where A corresponds to the yellow shaded area in the graphic and B to the arrow with the red fill. So during the months of January through April inclusive, water levels may be measured directly within the soil profile pits or borings. So whenever the department determines that there's been a significant departure from normal climatic conditions, the department may, with due notice to the administrative authority, lengthen or shorten the period allowed for direct measurement during any given year. In low-lying coastal areas where groundwater levels fluctuate with the tides, measurements shall be taken at the time of highest groundwater elevation in response to tidal fluctuation. But please take note that there's been no such change in the time frame for direct observation. During other times of the year, the depth to the seasonal high water table is obtained from the NRCS Web Soil Survey, provided that the soil series present at the site is identified based upon a comparison of soil profile morphology observed within a soil profile pit and the soil profile description provided for the soil series in question within the NRCS Web Soil Survey. So in cases where the seasonal high water table is shown as a range of elevations in the Web Soil Survey, the highest elevation of the range is used as the seasonal high water table. So this means that for testing done outside of January through April, if you don't see modeling, you follow the instructions in item B on this slide. And for soil testing for determining seasonal high water table, the third worksheet in our Excel workbook may be helpful for recording your observations. So next up are the construction and post-construction oversight testing requirements. So during construction, regular oversight must be provided by the professional engineer to establish that the basin will function as designed. And oversight includes, but is not limited to, the following: a pre-construction meeting with the contractor or contractors, confirmation of the proper use of construction equipment, especially to minimize the compaction of the infiltration area, ensuring that the earthwork does not occur within the BMP area when the soil moisture content is above the lower plastic limit, and that the specifications of any replacement soils is or are met as the case may be. And lastly, ensuring that proper precautions are taken to prevent sediment entering the infiltration area during construction, or where unavoidable, if the basin is used as sedimentation basin, excavation for the sediment basin is at least 2 feet above the final design elevation of the basin bottom. Post-construction soil hydraulic conductivity tests must be conducted to ensure that the installed BMP functions as designed. This is part of the design criteria in many subchapters of the BMP manual. All right, such testing must be carefully undertaken when all BMP construction that may affect soil hydraulic conductivity has been completed. This includes the use of all construction equipment and the placement of all construction material that may affect the soil hydraulic conductivity. In addition, hand tools and manual permeability test procedures must be used to avoid affecting the soil hydraulic conductivity. And the required number of tests for post-construction testing are as follows. So the number of tests must follow the same requirements as the requirements for the pre-construction soil hydraulic conductivity tests. And for the required test depth, the post-construction hydraulic conductivity test must be conducted at the bottom of the excavation of the BMP before the sand layer or soil bed is placed into the BMP. The permitted test methods for post-construction testing are as follows. Only the single ring infiltration test, the basin flooding test, and the double ring infiltration test or a similar test that doesn't require a test hole in the soil layer are allowed. The tested soil hydraulic conductivity from the post-construction hydraulic conductivity test must be equal or greater than the tested soil hydraulic conductivity of the most restrictive soil layer that was tested in the pre-construction condition. And lastly, all post-construction soil hydraulic conductivity tests results must be certified by a licensed professional engineer, submitted to the review agency, and recorded in the as-built documents. All right, so far I've covered the requirements for the soil testing that will provide the information on the hydrologic soil group that determines the runoff on the site, for the saturated hydraulic conductivity that determines the permeability of the soil underneath the basin, and for the seasonal high water table that determines if the BMP can be drained at all. So I think by now you'll agree that soil testing results are an essential part of stormwater management design. Furthermore, since exfiltration is allowed in routing calculations for infiltration BMPs, the volume and flow rate of runoff that can be actually infiltrated into the subsoil will affect the sizing of the BMP and the outlet structures. So more than ever, soil testing results that correctly describe the soil characteristics are really important. So let's address what's required for submittal with the stormwater management report. The reviewer should check that the following is included. Okay, web soil survey showing the HSG, location of the soil profiles and/or the soil borings, the soil test logs, including all of this information. And lastly, the hydraulic conductivity testing records. Okay, so that's just about everything I have for today. I see that we had a question about perched water conditions, and I didn't want to get into that today. So please see section 1E of chapter 12 in the BMP manual. But what I did cover today includes why we need soil testing, testing to determine HSG, testing required for infiltration Bs and also for the non-infiltration BMPs, testing to locate the seasonal high water table, and your soil testing requirements for construction, and post-construction. And lastly, I included the information that you should submit or see submitted in a soil testing report. So please, as a reviewer, check each and every part of the soil testing information for accuracy, since this is royally going to affect your BMP design. Okay, and when we get to the examples in Module 4, we're going to include some of these checks in detail. All right, so, but please check the website back so that if and when there are updates, you'll be ready to see those, okay? Just periodically check and refresh your browser. Okay, so you can reach out to me or any of the guys in the unit. They're all smarter than me, so please, we are there to provide help for you. All right, so here's the website and the unit contact information. And I'm going to ask Chingy at this point, if there are questions. If you don't think of anything right now, you can email them to us, okay? Not just me, but I think you have our email address all over the website. Chingy, what do you think? Are there any more questions?
I don't see any other questions.
Oh.
I think we can continue to invite Dr. McGee to give us the MTD presentation.
Okay. All
Thank
right.
you.
Well, then thank you everyone for your attention, and thank you, Chingy. So as he said, our next speaker will be Dr. Richard McGee from the New Jersey Corporation for Advanced Technology, and he's going to discuss the NJCAT DEP partnership for the verification and certification of manufactured treatment devices. So good afternoon, Dr. McGee. I'm hoping that by now you've turned on your microphone. Just let me know when it's okay to move on to the next slide. Perhaps one of my colleagues can unmute him.
I see Dr. McGee in the lobby. His mic is muted, but I don't see an option to unmute him. I think he's only able to do it on his end.
Okay, I'm going to go to the settings. Please bear with us, folks.
Am I out now? Am I unmuted?
I
Yes,
hear
you
now.
are.
Okay. All right. It was hidden someplace else. It wasn't in the standard one. Okay. So we're ready to go. All right.
Okay.
Well, thank you, everybody. I know it's been a long time. We've learned a lot, and I will welcome this opportunity to talk about the Stormwater MTD Verification Certification Program. I've listed 6 bullets up here of what we're going to cover. I can summarize them. The first 2 bullets will basically be a brief history of the program and the role of MTDs in meeting the requirements of stormwater management rules. The next part will be the actual program itself and some examples of the technologies that have been verified, certified, and the importance of that will be to point out things you've got to look for. And then finally, as a heads up, what are some of the misuse of the certifications? Not so much in New Jersey, because you guys are pretty savvy, but more so outside New Jersey, since this program really has a national impact. And then finally, the program continues to evolve, and I want to bring you up to date on where the status is and what you need to be looking at for in the next year or so. Next slide. And some background material. In the late 1990s, discussions began between then Commissioner Robert Shin, former Governor Jim Florio, and the Stevens Institute of Technology President Hal Ravachey for the need to support the development and promotion of innovative energy and environmental technologies, or what are known as IEETS in New Jersey. These resulting discussions led to the 208 legislature, which convened in July 1, 1999, to establish a technology verification program through what's called Senate Bill number 1750, to establish a technology verification program which would be administered and implemented jointly by DEP and NJCAT, and very kindly appropriated $95,000 to kickstart the program. I will say that they have not given any money since that time So the program has been self-sustaining. Next slide. The next activity that occurred was the Public Law 1999, Chapter 400, which became known as the Energy and Environmental Technology Verification Act. It was approved on January 18th, and it supports the development and promotion of innovative energy and environmental technology. But more importantly, it outlined the roles and responsibilities of the state of New Jersey, DEP, and NJCAT. Next slide. Finally, final activity that occurred in the year 2000, which kind of took all that prior work and pulled it together, was a signing of a performance partnership agreement between DEP and NJCAT in June of 2000. And some of the directives of this was relevant to the stormwater program. We're basically going down to the second bullet. The DEP is required to consult and work with NJCAT to develop performance evaluation and verification procedures, processes, and protocols for the purposes of determining the application of use of certain IIETs, studying, evaluating, and verifying the benefits of these innovative environmental energy technologies, and basically trying to identify beneficial and innovative technologies that might require some assistance with regulatory pathways. And through the years, then we have been required, and we have done to promote the awareness of the EET program and to try to identify innovative technologies that might be candidates for performance evaluation and verification. I might add that not on this slide, but just last month, an MOU was signed between DEP, BPU, and NJCAT to work with BPU to achieve the state's greenhouse gas emission reduction goals. I realize that has nothing to do with what we're doing here, but we've done some work with the Department of the past with energy, and now we're going to move into the energy area as well. And this first initiative will be on ground source heat pump HVAC systems, but that's just for a heads up. Next slide. All this, as you know, it was a requirement in the stormwater area as a requirement of the US EPA, and the history and federal acts that predated the post-construction stormwater management program and MS4 permit requirements were presented, as I understand it, in Module 1. So that's a brief, quick background. So let us now move on to focusing on the major subject, next slide, of this presentation, which is on manufactured treatment devices as their part of the best management practices, or BMP, found in the stormwater rules. So as I've said, the manufactured treatment devices are a subset of BMPs. They are proprietary, prefabricated stormwater treatment systems that rely upon a variety of mechanisms to remove pollutants from stormwater runoff. And they utilize very standard techniques of particle settling, filtration, sometimes through organic or inorganic media. They can enhance it with vortex separation. Some can use vegetative components or any other appropriate technology that would remove pollutants from stormwater runoff. I might say at this point that the focus in New Jersey has been solely on TSS removal, or total suspended solids removal, but there is movement in other states, particularly in Maryland, to do things with nutrients, such as things as phosphorus and whatnot. In some other cases, heavy metals. Those are not right currently a focus in New Jersey. Next slide. Okay, I think you all know at this point that the New Jersey Stormwater Management Rules, which are found at NJAC 78A, require major development projects to remove 80% of the project's TSS runoff on an annual basis. The rules also require green infrastructure, which are GI BMPs that manage stormwater close to its source by one of three means: treating stormwater runoff through infiltration into the subsoil, treating it by vegetation or soil, or storing stormwater runoff for reuse. We'll talk a little bit more about that as we get into to where we are with green infrastructure later on. Also, when you go to the stormwater rules in NJAC, you'll see that provide our TSS removal rates for both BMPs and MTDs. And as you know, the EPA requirements for sediments is 80% removal. And what is our role and what's the partnership? Our job is to verify treatment removal rates for MTDs, which are then certified by NJDEP. So it's a clear partnership. Next slide. So what is this verification program? Well, we conduct an independent third-party evaluation program that will verify the performance claims. We do that by having test reports submitted against the test protocols. We analyze that data. We ensure compliance with the test protocol, and then we issue a verification report, and we'll talk a little bit more about that. Excitingly, and I think to New Jersey's credit and how it has strong national and international recognition. Many states have kind of piggybacked on the work of New Jersey, and they asked the question, and we'll talk about that. Is this technology NJCAT, NJDEP verified, certified? These stormwater MTDs are evaluated against, as I've said, test protocols which have been developed by the department. First one that in great detail was put together in 2013, and they've just been updated in the last couple of years. There is one for hydrodynamic sedimentation MTDs that was published, and we'll talk about why it was updated January 1st, 2021, and then or issued and then updated in April 25, 2023. And that was more to do with basically validating the performance of many of the analytical laboratories relied on. TSS, HDS, removal efficiencies are targeted for HDS at 50%. Filtration MTDs, they came in a new one came in about a year later in 2022, again updated again for the analytical laboratory proficiency testing, and you can get removal rates up to 80%. Now, very importantly is this is bullet 4. Stormwater MTDs that are verified by NJCAT and DEP certified are the only MTDs that can be used to satisfy the requirements of the stormwater management rules for major developments. Currently, if you go on the NJDEP website, which is has the link below there, there are 14 hydrodynamic separators, 14 filtration devices, and 11 green infrastructure technologies that are currently listed. You might say, but wait, that hydrodynamic separators, if you notice on this table, that of the 14, 9 have sunset dates in 2024, and 1 in 2025. The reasoning behind this is why did we change the test protocols in 2021 from the previous test protocols that were in 2013? And frankly, we found out that the industry learned to game the original test protocols so that they could back up sediment in the inlet pipe to the MTD, deposit sediment there, and get credit for it. Particularly at low testing rates. And the problem with that is it doesn't really evaluate the ability of the technology to take sediment out of the stormwater. And that sediment may eventually get washed in at higher flow rates, or in drought periods, it may cake and build up and actually reduce or restrict the inlet pipe to the MTD. It became obvious that the testing people were clever enough to do that. So now the only credit you get is for sediment that is captured in the sump of the MTD. So we had to give people a certain number of years to recover the cost of testing. And due to that, there are sunset dates. And by the way, 11 have already sunsetted. So at one time, that 14, you could say was 25, but that's not exactly correct because some new ones have come in of the 4 there that will not sunset because some of them have been tested to the new test protocol. So you have to be very, very careful when people say that this is NJDP certified and NJK verified, both together to be used in New Jersey, that they are on the currently certified list. Next slide.
I was just going to show them the table. So
okay.
if you go, yeah, if you go to the stormwater page at the top, give me 1 second. Let me make this a little bit bigger. You will find the current listing. So it's under our stormwater page under MTDs, and you will find not only the ones that are listed first as green infrastructure and the conditions for them, but you will find below that the current MTDs that are not considered GI, and where there is an expiration date, it is listed here. Now, if something expires, it is transferred to the archive page. And that is, so this comes into play where you might have to modify a project down the road. You should be able to get the sizing information from the archive page where we keep those letters. If you have any questions, you can ask me. Okay, so I just want you to know that it's all here and I keep track of it. And we have the old O&M plan and we have the certification that expired. But if it's on the previous page, it's currently certified until any date listed in this column. Okay, so I do apologize for the interruption, but I wanted people to know that we updated the web page. So
that's very helpful. There's also if you go to the njcat.org webpage, you will see a listing of all that, and I'll talk a little bit about more of that later on, and they're archived. And because there's been some confusion in the industry, yeah. I'm not sure whether that confusion is with DEP also. Why are certain technologies in certain areas and why are they being sunsetted? Because the industry was not crazy about sunsetting in the sense, not some of them, because they've invested money in it. On the other hand, it is also clear that that the sunsetting is resulting in an improved performance in some of the new ones coming in. Frankly, it has spurred some innovation from my viewpoint, and I think that's what we're all trying to do in this business, is to get the best technologies out there. You may have some questions later on in this subject, and if so, please add them to the chat, and between Lisa and I, we'll be more than happy to answer them for you. if we can go back to the presentation, Lisa.
Absolutely. Yeah, I was
You
just going to
have-
show them that, yeah, there's even a link to Dr. McGee's page. And so
Yeah, and
with
that's a
that,
link there, and you'll see that in my page, there is a detailed discussion that leads you through, and on here you'll see them broken up into GIs, HDS, and then you'll also see another page of archives. So between those two, you've got to. And by the way, on my page, you'll also be able to get the full verification report, which typically runs 40 to 50 pages. A lot of good material in there. Not many of you are going to want to read them, so I'm going to tell you as we go through here some of the things you got to really watch out for.
okay. So with that being said, we're going to move on to the next slide in the presentation when you're ready.
I think so.
Okay.
All right, now what I want to do here is I want to just show you some of the 4 different technologies that have been verified and certified, but I want to use them as an illustrative point. Here you see what's called a debris separating baffle box. The first thing I want you to note is that the inlet and the outlet pipe are aligned, okay? So if however you want to call alignment there, and why is that important? And I'm going to re-emphasize this because a lot of plans that have been sent to me that people have put into New Jersey show MTDs with inlet outlets that may not always be aligned in the way they are for the test. So this is how this unit was tested. Sediment came in from the left-hand side, goes out the right-hand side. You'll see the sediment, this is due gravity separation. So it drops down below, and you see below you've got these baffle walls below, 3 different compartments where you can collect the sediment. If you go to the next slide, you'll get a top view of what's going on, and you'll see why it's so important that the flow come in directly and along the line, because what's happening is you hit a splitter, a screen, stuff that floats, debris catches on top of the screen. As the stormwater continues onto the device, it not only contains sediment. Sediment drops out to clean stuff in the center, but sediment also drops out along the side because obviously there's sediment with the streams that are being separated on either side. They then go down beneath the that wall and come out the other side and come out the outlet pipe on the other side. So that's one example. Next slide. This one shows you a manhole. Many of these are inserted in manholes. Again, you'll notice the inlet and outlet pipe are aligned. If that were a face of a clock, you might argue it's coming in at 9 o'clock and going out at 3 o'clock. But in any event, it's very critical to how this device works that those two be aligned. And I'm going to come back to that later on because this is a very important point. You've also got a manhole cover, a flow splitter, excuse me, sump and whatnot. Go to the next slide. You'll see a little bit more about how it works. This one enhances what's called vortex separation. You can see the stream comes in from the left. It hits a diverter plate, separates into 2 directions, which then causes a circulating vortex motion on either side. If you go back to the previous one, that then goes down below that plate, allowing for settlement, comes up the other side, and then goes out the outlet weir on the other side. So it's pretty effective in doing. In here, there are perforated holes in that weir. That's why you see all this going top. And also, there are 2 larger holes, which will also allow flow to come up underneath. The point of it is, all these devices are designed to capture and then retain any of the sediment down below. Next slide. Filters. Filters are another important MTD that are used to remove sediment from stormwater. This one shows you 2 cartridges in a vault. The vault is broken up into 2 sections. There's kind of like a pre-treatment section, and then the material that goes from the pre-treatment fraction into the filter chamber. It then goes through those filters and back at the other end. Important, if you say this was one that only tested with 2 filters, but one can then use many filter chambers as long as the ratios are maintained proper. And what do I mean by the ratios? This is more detail than you know, but you got to maintain the ratio of the pre-treatment chamber to the size of the treatment chamber, which has got the cartridge in it. You want to keep that ratio larger than is tested in the test unit. You also want to make sure that the sedimentation area around the cartridges is larger in the tested to the filter ability, so you're not putting too much on the filter, too much of a sediment load. All that, however, you don't have to deal with, because that's the models that have been are certified have already been verified, the charts, and they're all in the certification letter. Okay, next slide. Finally, probably the biggest innovation that's occurred are what are called green infrastructures. And in here, you have a curb inlet coming in on the left-hand side into some soil media, which could include planting also. The soil media then filters out the stormwater, and the filtered stormwater then leaves to the right to say, for example, a stormwater drain along the way. And these are becoming very, very popular. Next slide shows you a little bit more detail of what's like. You've got a mulch or planting layer above. You've got an engineered media beneath that. You then have stone usually on the bottom and a perforated pipe that goes out the other side. There are some GI technologies that want to infiltrate directly into the ground as well as through the perforated pipe. And you have to look very carefully at the certification letter, because currently they're requiring 100% of that material. If you're going to infiltrate to the ground, it's 100%. In other words, they do not appear to allow for a combination of the two. And currently have discussions underway with the department as to is that overly restrictive. But right now, read the certification letters. Next slide. Okay, now we're getting to the point that's important. How are these certifications misused? And I'm not sure the manufacturers are, but certainly the sales representative or the manufacturer's reps want to do it. First of all, I want you to realize that not all NJCAT verified MTDs are DEP certified. And why is that so? Well, there are jurisdictions outside New Jersey that are willing to accept a coarser particle size distribution, what we call a larger D50. We require in New Jersey a D50 of 75 microns, which means that 50% of the sediment is by weight is below 50 microns, 50% is above. And some are willing to accept a larger D50, maybe 110 microns. And you say, well, rather than 75, you say, well, why is that so? Well, because they don't like filters and they think filters are hard to maintain. So they're saying, well, you know, we'll accept a hydrodynamic separator that can separate 80% if they, you know, on a larger particle. Or obviously, you could get away with a smaller unit if you're only trying to get larger particle size out. So you got to be very, very careful. It's not going to be a problem in New Jersey as long as you look at the DEP list of certified technologies. As I mentioned to you right now, only 11% of the currently certified technologies are GI certified, but this is a growing number, and I expect to see more and more of this in the future because the regs in New Jersey require you that you have to show you cannot use a green infrastructure technology before you can get approval for an HDS or a filter technology. And probably the biggest thing that I see coming in the area is that people want to use an HDS, hydrodynamic separator, in a configuration that was not tested as part of the certification process. And what are some of the exclusions that I see? One is I see site plans being sent to me where the inlet out configuration is not 180 degrees apart, as I showed you in those other diagrams. To be sure, you might have one coming in at say 45 degrees off of that horizontal line. Well, depending on the technology, there's no guarantee that you're going to get the same result. Others I've seen having come in with multiple inlet pipes, 2 in the site design. Obviously, that's going to change the fluid mechanics inside the device and its performance. And finally, in some cases, people have a great inlet, a drop-down inlet, which is entirely different than the technology that was tested, verified, and certified. So you have to be very, very careful that you don't see any of those 3 things coming in a site plan, that i.e. the inlet outlet are not 180 degrees apart, multiple inlet pipes, or a great inlet. All right, next slide. The other thing that can be a misuse of the certifications is whether or not it's certified for offline only, or it can be used for offline and inline. And to do that, you have to show, if it's going to be online, you have to show that you can retain the captured sediment. So you have to run a scour test. If you choose not to run the scour test, or for an HDS, you don't run it at 200%, then the certification is only for offline. And this will be listed in the certification letter, which is posted on the NJDEP website for any of those technologies. So make sure that if it's not shown as offline installation, that it is in fact then certified for online. I don't know of any filters, I think, that are certified for online. There are some HDS that are, however. Next slide. Okay, the exciting thing about this program is it continues to evolve. As I mentioned to it, NJCAT has been involved in it for over 20 years. Protocols have changed. They've gone from a program that was based on field evaluation to one that was on laboratory, to field, back to a protocol that was put in 2013, which was laboratory, which I said has now been sunset because manufacturers learned to shall I say, circumvent the intent of the protocol, till we now have a new set of protocols. So we have an expanded and added explanatory text. Lisa showed you that. These technologies that are verified and certified are broken down into 3 categories. And as I've told you, the HDS, the hydrodynamic separator MTD, is evolving quickly, and that's going to have new additions and removal additions next year, so pay attention to it. There are some laboratory verified technologies which don't really fit the program that well, and some were under the old protocol. They will sunset this year, so that list will be very, very small at the end of the year. If you're interested, Any technology that goes through NJCAT verification program that wants to be certified has to be posted for public review, a 30-day review period. The industry polices this very, very heavily. Any objections to the review are either overstatements or if I've missed something in the review process can be challenged. And I cannot move a report out of public review to the department until I've satisfied all public review comments. In some cases, just a few, they have had to go back and do some retesting before I could move it forward because some of the review comments were substantive enough, and frankly, I shouldn't have let them get to that point, I don't think. But it provides a very, very robust review process. And then there's some additional energy environmental technologies. As I said, there's also an archive page now, both for the department and for DEP, for JCAT. And as verification reports get sunsetted or are no longer verified, they've been moved to an archive category. Industry asked that that be done, and it makes sense only because they spend a lot of money. And frankly, other states may accept results from a previously verified protocol, and whatever that agency that has jurisdiction on the thing, they can do that. But none of these can be accepted for use in New Jersey. So you need to know that. And finally, I think the last slide is what about the program moving forward? It's going to be a heavy year next year managing the implementation of the new HDS protocol because all these other technologies, many of them will have sunset by then. We've already sunset 11 of them. There'll be 10 that'll be sunset in the next year or so, well, 9 and 1 the year after. But anyway, as we've transitioned into this new HDS protocol, it's a matter of moving sunset technologies off into new categories and bringing new ones on because many of the technologies that were previously certified want to remain certified. But as I'm hearing from the industry, they're tweaking their technologies to improve their performance, which is good. There's a new ASTM, American Society of Testing Materials Committee, established that are based on ASTM standards. And frankly, these are right now heavily based on the NJDEP test protocol. In fact, they're meeting in Baton Rouge today, and I'm not there because I'm here. I wouldn't have probably gone there anyway. Again, there will be 8 HDMTDs that were verified only. They'll be sunsetted 4 in December and 4 by next year. And then finally, there is a stormwater testing and evaluation for products and practices called STEP Initiative. It's heavily manufacturer driven. They're trying to make it a national program. They only allow those manufacturers who pay a heavy dues to get in to vote. They do not have a robust evaluation procedure yet for anything. And right now, what they have voted to do is to move NJDEP certified technology onto their list of certified technologies. In other words, they're piggybacking off of this program, which makes sense because it's a good program. I thank those at DEP that have worked with me to make it what it is. And it's one I think both the department and NJCAT can be proud of. Lisa, at that point, I think I've met my time constraint, and I'm willing to answer any questions if anybody has them. And I hear silence.
I don't see any questions. So we really thank Dr. McGee give us this presentation. And Peter, we are moving on the quiz, and thank
Yeah, thank you,
Dr.
Changi.
again.
And
Thank you very much.
I again would encourage anybody at any time to contact NJCAT. We have our contact through njcat.org. Happy to talk to you. I'm excited about this program. But people like Lisa and Changi know this program as well, so they can probably answer questions directly. But happy to talk to you. And thank you again for this opportunity.
Thank you.
Thanks, Dr. McGee. So
All right,
as Changi said, oh, go ahead.
Okay, I'm going to leave.
All right, you take care. Thank you again.
Bye.
So up next is Peter with quiz 2, and we will momentarily provide you with the QR code in the chat so that you can take your camera on your smartphone if you wish and aim it at that. But if you're on your computer, as a reminder, you're going to open a new window or a tab so that you're not booted from the meeting. So please stand by while I hand control over to Peter.
Okay, good afternoon, everybody. It is now time for quiz number 2. As noted before, it is important to complete the quiz now during the time allotted. Note that you cannot move forward to complete a quiz or complete a quiz at a later time. And we need the quizzes to be completed in order to issue credit for the class. So let's get to the quiz. So just like Tuesday, there are a few ways to get to the quiz. The link in the middle of this slide will take you to a page on our website, which includes the handouts as well as each of the quiz links. You can click the link for quiz 2 found at the bottom of the page to be taken to the quiz in SurveyMonkey. Another way is using the link at the bottom of this slide, which will also be posted in the chat, as Lisa said, to be taken directly to the quiz in SurveyMonkey. Make sure to do this in a separate tab in your web browser if you choose that option. And then lastly, if you want to take the quiz on your phone, you can scan the QR code on this slide, which is also in the chat, and you'll be taken right to the quiz. And just a few other notes on the quiz. So you must answer every question before you can advance to the next screen and finally submit. You may only take the quiz once. And we're going to allow 15 minutes to take the quiz. So it's 3:32 right now. So we can just give to 3:48. We'll give to that time for you guys to complete the quiz. And if you finish early, you can feel free to take a short break. And then after that time, we will review the answers to each question from the quiz. The review portion of the quiz is part of the course and for credit and attendance, so please do not leave after completing the quiz. We won't keep you for too long. Here's everything in one place. Please begin taking the quiz, and I'll come back for the review at 3:48. Thank you. All right, hello again. We're going to start the review a little bit early to make sure we can get through all the questions. The quiz is still open, so if you're finishing up, you can finish up those last few questions and make sure to hit submit. And we will go ahead and get started with the review. Now, the first 3 questions on the quiz were general information type questions, so we will begin here at question number 4. True or false? There is no longer a minimum or default value that can be used for time of concentration using the NRCS methodology, meaning this value must always be calculated. That is true. There is no longer a minimum or default value that may be used for the time of concentration. The time of concentration, or T sub C, for pre- and post-construction conditions must be calculated based on the flow path. As you recall, Anthony went over this in the first presentation from today in the calculations. Number 5, according to the NJ Stormwater BMP manual, what is the maximum roughness coefficient that can be used in sheet flow calculations for wooded conditions in New Jersey? Correct answer is 0.4. The maximum roughness coefficient that can be used for wooded conditions is 0.4. Though the National Engineering Handbook lists Manning's roughness coefficients as high as 0.8 for woods with dense underbrush, for New Jersey, the maximum roughness coefficient for sheet flow that may be used is 0.4. New Jersey does not contain land cover that supports the use of roughness coefficients associated with woods with dense underbrush. Number 6. What is the maximum sheet flow length for the pre-construction condition, assuming there is no physical constraint present to prevent sheet flow from occurring? B, 100 feet is the correct answer. For the pre-construction condition, the maximum distance for which we can assume sheet flow occurs is 100 feet, unless there is something physically in contact with the flow of stormwater runoff, such as a swale, curb, or inlet, to prevent sheet flow from occurring. Remember to use the actual distance if it's less than 100 feet. So this comes from Chapter 5 of the BMP manual if you have not taken a look at that yet. And another reminder to make sure to use the actual distance if it's going to be less than 100 feet. Number 7. According to the stormwater management rules effective on July 17, 2023, which methodology can be used in the computation of stormwater runoff? The correct answer is NRCS method. The stormwater management rules effective on July 17, 2023, removed the rational method and modified rational method from NJAC 7:8 and only allows the NRCS method to be used in stormwater computation. Number 8, true or false? When using the NRCS methodology for directly connected impervious cover, averaging pervious and impervious curve numbers is permitted for calculating a hydrograph. This statement is false. Here's a quote from NJAC 7:8 5.7A4. In computing stormwater runoff from all design storms, the design engineer shall consider the relative stormwater runoff rates and/or volumes of pervious and impervious surfaces separately to accurately compute the rates and volume of stormwater runoff from the site. This statement does not apply when using the NRCS composite CN with unconnected impervious area method. See Chapter 5 of the BMP manual for more information. Question 9. When determining the curve numbers for site design, the design engineer should assume that the condition of the existing cover is good condition. This is fairly straightforward. Pre-construction condition curve numbers should assume that vegetated areas are in good condition. Number 10, yes or no? Can the Delmarva dimensionless unit hydrograph be used for the redevelopment of a 2-acre entirely impervious site located within the coastal plain? The answer to this is no. The Delmarva dimensionless unit hydrograph must be used when modeling watersheds within the coastal plain region of New Jersey, with just a few exceptions. It cannot be used to size a manufactured treatment device or MTD, as it may underestimate the peak flow rate entering the MTD. Also, for an entirely paved site, the significant surface storage associated with the coastal plain is no longer present, also resulting in underestimated peak flow rates if the Delmarva is used. Additionally, the Delmarva should only be used in areas that have an average watershed slope less than 5%. If any of these situations are proven to be present, the SCS standard dimensionless unit hydrograph must be used. And a side note on this subject, if the Delmarva is used in the pre-construction condition, it must also be used in the post-construction condition. Same idea goes for the SCS. Question 11, true or false? When using the NRCS methodology for calculation of stormwater runoff, the Type 3 rainfall distribution must be used for developments in New Jersey. That is false. As heard from Anthony today, NOAA C or D distributions must be used, not the Type 3. Number 12, true or false? Pretreatment must be incorporated into the design of a small-scale GIBMP that has a that has a drainage area greater than 1 acre, infiltrates runoff into the subsoil, and uses exfiltration in the routing calculations. That is true. All small-scale GIBMPs, which are designed to infiltrate into the subsoil and have contributory drainage areas greater than 1 acre, must include pre-treatment of stormwater runoff when using exfiltration in the routing calculations. Number 13, soil testing logs prepared in accordance with Chapter 12 are required for which of the following BMPs? The answer is all of the above. They all have a minimum separation from the seasonal high water table, which you can find in their respective BMP manual chapter. Soil testing will therefore be required for all of these to ensure that they meet the required separation. Question 14, true or false? Factor of safety of 2 must be applied to the slowest tested saturated soil hydraulic conductivity rate to determine the design saturated soil hydraulic conductivity rate, which is used for infiltration BMP calculations. This is true. Since the actual saturated soil hydraulic conductivity rate may vary from soil testing results and may decrease over time, a factor of safety of 2 must be applied to the slowest tested saturated soil hydraulic conductivity rate to determine the design saturated soil hydraulic conductivity rate. Computing a BMP's drain time for the maximum design volume, the exfiltration rate for a BMP allowing exfiltration in the routing calculation, or the infiltration rate and the groundwater mounting analysis must all use the design saturated soil hydraulic conductivity rate. Okay, number 15, yes or no? During the month of July, Can the seasonal high water table be determined by measuring water levels directly within soil profile pits or borings? The answer to that is no. So you can determine the seasonal high water table by measuring water levels directly within soil explorations between January and April only. Other options to locate the seasonal high water table include observing modeling showing redoxomorphic features, which can occur any season of the year, and using the NRCS Web Soil Survey during the months of May to December. All three options have their own steps and exceptions. See subsection 1D of Chapter 12 of the BMP Manual for full details on each option. Question 16. When is it necessary for the design engineer to assess the hydraulic impact on the groundwater table? And the answer is whenever an infiltration BMP is proposed. You should assess the hydraulic impact on the groundwater table anytime an infiltration BMP is proposed. This would include any potential drainage issues and potential damage to nearby structures. Number 17. How many soil profile pits and/or soil borings must be performed for 5 small-scale bioretention basins and 1 mapping unit that are each 450 square feet and scattered around a development? The answer is C. So we know from Lisa's soil testing presentation that if an infiltration BMP has an infiltration area that is less than or equal to 500 square feet, you would have to do a minimum of 1 soil profile pit per soil mapping unit. You would also have to do 1 soil boring per BMP as well. If the BMPs are going to be located in different soil mapping units, each unit must have 1 soil profile pit. But if you read the question here, the 5 basins are going to be in 1 mapping unit. So in total, 1 soil profile pit for the 1 mapping unit in this example, and then 1 soil boring per small scale bioretention basin. Number 18, true or false? In a small scale infiltration basin, the 2-foot separation from the seasonal high water table should be measured from the surface of the sand layer. This statement is false. As stated in the BMP manual, for any designed infiltrating BMP, the separation from the seasonal high water table needs to be measured from the bottom of the sand layer, which is the lowest excavated elevation in the BMP. We mentioned the seasonal high water table separation requirement when we talked about why the soil testing is important. Number 19. Where on the soil horizon should soil permeability tests be performed when no soil replacement is proposed? Correct answer is A. Soil permeability tests must be performed on the most hydraulically restrictive soil layer below the BMP and above the seasonal high water table or bedrock to the greater of 8 feet below the lowest point of the basin or 2 times the maximum potential water depth, as the permeability of this layer will be the limiting factor in infiltration rates. Number 20, last question. True or false? When choosing a hydrodynamic separator type MTD, the inlet configuration, such as the angle and number of inflow pipes, must strictly match the inlet configuration described in the NJCAT verification report. That is true. Manufacturers will try and offer other types of configurations, but this is not allowed. They must not deviate from the tested and certified configuration that the MTD was meant to be in, as they would not meet the certified TSS removal rate. Okay, so that is the end of the quiz review, and that's also the end of Module 2.